Okay, those of you who have been doing materials lab in Reynolds, are you back? Or there was no lab today? So nobody who did lab until 5 o'clock is here. Okay, so probably I'm not going to start as such, but I'll show you probably what's our plan for the tomorrow and week after. So you have probably seen this tutorial on statics, which is a collection of problems, of beam type of problem, and for which there are some numerical answers given. You are highly encouraged to do this tutorial set on your own, because this would be forming the basis of your concepts, how to calculate the reaction forces, how to do equilibrium. Any problem you will be solving in this course probably start with the variations of the problems are given in here. Okay, so make sure that you get it, and you don't need to solve hundreds of problems as long as you understand the principles and the concepts. So please do so. I will release the solutions later on once you have tried. And for tomorrow tutorial at 4 o'clock in this building, I think different room, there are two examples problems are given here, one for aerospace students and one for civil engineering student. So there are three problems for the civil engineering students to do, and similarly there will be three problems for aerospace engineers to do. Now you can have a look at these problems today if you have got time, or tomorrow morning if you have got time. But once you are here, what we'll do is we'll encourage you to think about this problem, or if there is any difficulty, there will be 5 other GTAs. So we'll go around the room. I don't know what the room is it flat or gallery, but flat would have been better. But anyway, so we'll go around and give you hints on how to approach the problems. So idea is that you get the concept right and you ask the question which is related to the understanding of the problem. So it's not as much as coming up with a solution with numerically correct answer, which is important by the way, but it is more important to understand this problem. So make it as a tractable problem. I will release the answers after the tutorial. So tomorrow evening you will get answers to all these problems, all these 6 problems. And finally, if you are an aerospace student, look the problem sets for the civil students as well, and vice versa. So these problems would be, although they look different, but essentially you will see the principles being involved are exactly the same. So if you are analyzing an aircraft, or you are analyzing a cable mast, for example, system, it's essentially the same principles you will be using. So that's about what we are going to do tomorrow. In terms of your final assessment, I'll probably give you more details later on, but what we are going forward is it will be an online assessment. So not pen and paper, of course you need some pen and paper to do, but it will be online assessment in January, and it will be in a computer cluster. Okay, so not from your home, but in a computer cluster under invigilation condition, but you don't have to write on piece of paper, so it would be different types of questions. So we'll go through that, but that's what we have decided, and I thought I'll let you know that I said that most likely to be online, so it will be online in January exam. Okay? But you will have few dry runs with the assessment during the term. So you'll have 4 assessments during the term, and you will have some dry run and notes through those as well. So all those term time assessment will have also weightage associated with it, and finally there will be a group work which we'll discuss according to the timetable. So are you the lab guys? You have done labs in coming back from the labs in Reynolds, are you? Yeah, good. Okay, so we can start now. So what am I going to do is I'm going to go through some of these problems one by one, and then or at least a few. If you have got any question and want me to stop, want me to do it another way, want me to explain again, please do so. As I said, this particular tutorial set is very fundamental and it's important that you get it. Now, how many of you have tried at least few problems on that? Can you raise your hand, please? Have attempted at least this tutorial? Good, very good. So I'm quite pleased. That's very good. Very good. Thank you. Those of you who haven't, please do so as soon as possible. Because if you fall behind on this, then it will be difficult for you to catch up when we pick up speed. So first of all, what I'm going to do is I'm going to solve a couple of problems. So the first problem, problem 1A, we did last week or this week on Monday. So I'm going to do the second problem, 1B, and see what we can do. Okay. So 1B, so this is okay. So this is tutorial set 1. And problem 1B. Okay. So you have got a problem of shown a beam, and I'm going to use a ruler. So you have got a 7-meter long beam. So you have got a 7-meter long beam, and with 2 supports, 1 pin support at this end and 1 roller support the other end. Now roller support, sometimes instead of putting the triangle and then the roller as shown in the diagram there in point 1B. So if you concentrate on this diagram, you'll see this is a pin support and this is a roller support. So it's same thing as a pin, but with 3 roller at the bottom. Instead, sometimes for shortness or brevity, people just put a roller, showing that it's a roller support. So this is a pin support and this is a roller support. So pin support means it will not let any movement into horizontal or vertical direction. Now of course there is a load onto it, and the load is from 2 meter to the 7 meter. So the load is from here, and it's uniformly distributed load. So this is uniformly distributed load, and as I said, people do it in both ways. Either they put those semicircles way, or they put a series of arrows. And these loads are 2 kilonewton per meter. That means the length of the load train is 5 meter here. So this is 5 meter. So the total load would be, so this is 5 meter. So the total load would be 5 times 2 kilonewton. So 10 kilonewton would be the load. in this case. So 10 kilonewton would be the load in this case. And then this is of course 2 meter over here. So this problem asks you to find out what would be the reaction forces in the support. So to get the reaction force, first thing you need to do is to draw the free body diagram. And you know what a free body diagram is. So first of all, the first step is to draw the free body diagram. So I write it there. So you need to draw a free body diagram, or FBD for short. So what do? First of all, you draw the beam itself, or the structure, whatever is given to you, you draw that. And then either you can think about taking off the loads, taking off the supports, one support at a time. So get rid of the pin support and replace with an equivalent force that may exist. So pin restricts movement in the horizontal direction. So once I take off that pin, I would replace that with a possibility of a horizontal force. Let's call that R1. R1, R stands for reaction. Pin also resists vertical movement, so I would expect a vertical reaction force. Let's call it R2. And similarly, the roller here would let free movement in the horizontal direction, so no force would be generated in the horizontal direction, but you could have a vertical reaction force. So let's call this R3. And next you put all the loads that is acting onto the system. So these are all the loads. So this is 2 kilonewton per meter. And 2 kilonewton per meter over 5 meter length. So we can now find out R1, R2 and R3 using our equilibrium equations. But one of the things when you have got an UDL, or uniformly distributed load, so this type of load are called in short UDL. This stands for uniformly distributed load. So it is UDL. So often it is useful to draw or to sum it up, and for this type of problem, when you are just doing the reaction forces calculation, then it is better to consider what is its net effect. So net effect means you sum up the total forces and put it into its action point. So I am just redrawing the diagram again, R1, R2 and R3, but this time I will make a change. I will put that load, all of this load, which was 2 kilonewton per meter over a length of 5 meter. So this length was 5 meter. So this was a 5 meter length. So the total load in this case is 10 kilonewton. So total load is 2 kilonewton per meter over 5 meter length. So that much kilonewton. So total load is 10 kilonewton. So for the sake of calculation, where do you think it would act? Now of course it will act in its center of gravity of the load. So where do you think center of gravity of that load would be? Now of course it is a uniformly distributed load, so it will be in the middle. So the middle means 2.5 meter from the right hand side. So 2.5 meter from the right hand side is here, and I would expect, so I'll replace that with a big arrow and I'll say this is 10 kilonewton and it is acting at a distance of 2.5 meter. So 2.5 is half of 5 meter over there. So if that is 2.5, total span was 7. So that would give me this one as 2.5 plus 2. So that would give me 4.5 meter. So that's it. So basic calculation is done. We can now find R1, R2 and R3. So how do I find R1 and R2 and R3? By using equilibrium equations. So let's do our equilibrium equation. So if I do equilibrium equation of summation of horizontal forces 0. So I'm going to consider our system as this one. So this is the one I'll consider. So summation of horizontal forces 0 would give me, there are 4 forces here, R1, R2, R3 and 10 kilonewton. So these are the 4 forces. So if I consider right hand side towards force is positive, then R1 is really the only force. So R1 equal to 0. Next, if I do summation of vertical forces 0, so let's say I take vertically upward as positive, then I have got R2 going up, 10 coming down, R3 going up, so that is positive, is equal to 0. So this gives me an equation which says R2 plus R3 is equal to 10. Now that makes sense because those two reaction forces must balance the vertical loading that is coming. But this doesn't give us what is the value of R2 or R3. So for that I need a third equation, which is a moment about a point is 0. Now this is important. Moment about a point is 0 could be any point. It could be this point, it could be that point, it could be this point, it could be outside the structure as long as in this plane. So it could be about a point here, for example. So you can do that, but sometimes using that point judiciously will make your calculations easier. Let's say this point is A and this point is B. If you take moment about point A, then you can get rid of R1 and R2. Because moment about point A due to R1 would be 0 because R1 passes through point A. Similarly, moment about point A for R2 will also be 0. So only thing would be a known 10 kilonewton force and a known unknown R3. So we can get R3 for example. So let's say moment about point A equal to 0. You could have done using moment about B equal to 0 as well. And let's say this time we will take also as before clockwise as positive moment. So if we do that, then so R1, R2, 0. So 10 kilonewton force makes about point A. So the point you are taking moment, hold your finger at that point. If you have difficulty in visualizing, hold that point about which you are taking moment. And think of each of the force one by one, how it is going to rotate the part of the structure. So the structure here is beam. Don't think about any other support. Don't think, okay, my beam really cannot go like this because there is a roller here. Okay. Now, why you shouldn't think about that way? Because the effect of roller you have considered through this force R3. So you will consider that. So maybe the tendency of 10 kilonewton force is like this, and tendency of R3 would be that, so that this balance is at this point, so no deflection at that point, but you will have deflection in the middle. So don't think about how it is supported. Only think about your structure and the point about which you are calculating moment. So point A I am calculating, think of that as a hinge and see how the force is going to rotate the structure. So this 10 kilonewton force will rotate it in the directions of a clock. So the moment would be positive. So what is the moment? Moment is the force times the distance. So 10 times 4.5, and this is a positive moment. What about R3? R3 will rotate the beam in the anti-clockwise direction. So it comes with a negative sign. So R3 times 7. These are the two, because R1, R2 will be 0. So that is equal to 0, which gives me R3 is equal to 45 over 7 kilonewton. So 45 over 7 kilonewton means whatever it is, you can do that. But if you go back now, put that value in the previous equation, then you can get the value of R2. Because from here, we know R2 is R3, 10 minus R3. So 10 minus R3 would give you 10 minus 45 over 7. So that is 70 minus 45. So that is 25 over 7 kilometers. So you now know R1, R2 and R3, all three reaction forces. This is what the problem is asking you. Find out the three reaction forces. So the horizontal reaction force 0 and R2 is 45 and R3 25 over 7 and R3 equal to 45 over 7. Now do have a quick sense check. So R1 is 0, yes, there is no horizontal force acting, so R1 is 0, that's right. R2 is lower than R3, does it make sense? Yes, most of the forces or load are on the right hand side of the beam. So R3 would have a larger share of the load, so which makes sense in here. So develop this sense check whenever you do the calculation. Don't always believe what you get from the calculator, because you may have mistake with your calculations there. So that is one way of doing this. So summation of horizontal force 0, summation of vertical forces 0, moment about a point 0. Could we get it into some other different ways? Of course we can. So let's try a different strategy. We will do three other sets of equilibrium equation. Let's say I'll do summation of force in the horizontal direction 0. That will similarly give me R1 equal to 0. That will give me straight away. I could also take moment about point A equal to 0, which I have done here. So that will give me the value of R3. So I'll get the value of R3. I'll get the value of R3. Now instead of a vertical forces 0, the equation here, if I have taken moment about point B equal to 0, that would have given me R2 value. So this is also a valid set of equilibrium equation. This is equally valid. Let's check whether you can do it something else as well. Let's start with moment about A equal to 0. So moment about A equal to 0, as before, will give me quickly the value of R3. I'll get that. Moment about B equal to 0 will give me value of R2. Now if I take another point somewhere which is not along a line A to B, so which is not along this line. So take a point C, such that it is not along the line AB. And if you take moment about C equal to 0, let's say point C is there, then you know R1, you know R2 value already, you know R3 value, so only unknown is R1, so this will give you the value of R1, because you already know R2 and R3. So moment about 3 points can also give you all these three unknown forces. So it is not a unique way of solving this problem. You can do it in many different ways, because this equilibrium equation comes in different flavors, different combinations as well. And depending on the problem, some cases one would be better to do than the other. Now, if in doubt, always do the basic one, the first one which we did, summation of horizontal forces 0, summation of vertical forces 0, moment about a point 0. That first set will get you through most of the problem. So start with this, and sometimes it is useful to try the second one as well, and third for some problem. Did everybody get it? Anybody who didn't? No? Okay, good. So that's the way to do for that problem. Now I'm tempted to show you how the beam would deflect, for example. Let me try to see whether I can get it through to solstice. Engineering A. Engineering A, lecture theatre A. Just give me a couple of minutes. 7831. Okay, so I'm going to show you a couple of, now again as I said, I'll show you some of the Android app as well, but as I bought this iPad, so some of these apps that I'm going to show you are Apple one. There are various versions of those, so let me show, maybe that one. Okay, so if I show you this one, let's say, and let me change the unit first of all. So SI close. Okay, so the length I want is 7 meter, and the load I want 5 kilonewton, and load location is 2 meter from the left, and 10 kilonewton. Okay, and the beam is this. So I'm not changing E or anything. So this is something called moment diagram, but let's say this is the so the beam would deflect in this way, and you can get, this doesn't show the reaction forces unfortunately, but you could see something called moment, which would be useful later on, and the rotations. Let me show you another app which has got the reaction forces. Yeah, this should do. This should do. Maybe. Okay. Okay, so this one I just was doing before you arrived. So this is the load, 2 meter, 5 meter, and the beam would deflect in this way, and you could see the maximum deflections amount depend on the material you choose, but also you can see the reaction forces. So reaction forces would be, in this case, 3.5, I'm doing the first problem, sorry. Should have shown you. Okay, so this is the problem. So this is how it is going to deflect, and the reaction forces would be like this, 1.79 and 3.21. So those are the doesn't sound right. The value probably this one is not right. Not 2 kilonewton per meter. This is 1. Okay. Okay, so now makes sense. 3.57 is approximately 25/7, and then the rest is 6.43 on the other direction. So you could use some of these some of these problems in here, using these apps, for example, for checking, and if it's fairly easy to do as well. So if you want to show some of the complicated ones as well to check your answers, you can definitely do that. Okay, so the next point, if I want to, I think I've done it in here as well, with the moment. No. Yeah, with the moment here is done. So problem C has been done as well. So this is how it will deflect, and the reaction forces would be in this way, minus 1.43 and plus 1.43. Now this, some of you, at least one of you told me you found it difficult for this problem to be solved, problem number C. And I have put in a video as well how to solve this particular problem. So I'm going back to my document here. So I'm going to solve this part C problem, 1C. So 1C is, again, the beam is 7 meter long. So the beam is 7 meter long, and it has got a moment, concentrated moment acting at 2 meter point. So a moment acting there, and the value of that moment is 10 kilonewton meter. And if you do the free body diagram for this case as before, so you will have two reaction forces here, R1 and R2, and you have got R3 in this point. So how do we find R1, R2 and R3? Now one of you came at the beginning and told me you find it difficult how to visualize this 10 kilonewton meter moment. Well, there could be various ways to visualize that. Imagine at this point you have got two sides of a conveyor belt, for example, attached at those points. So you could think about this problem something like if I draw it here, something like an arrangement. Let's say this point being here, and you have got maybe something like this attached into this way. So you have got a force going that way and force going that way. Let's say this force is, I don't know, 10 kilonewton, and the distance between the top and bottom is 1 meter, for example. So that would give you 10 kilonewton meter moment at that location. So this point is this particular point. So let me give a name. So let's say this is point A, point B, and this is point C. So this point is point C. So at point C, you could have an arrangement that way which gives you a 10 kilonewton meter moment. So two 10 kilonewton forces going opposite directions create a moment, localized moment at the beam, for example. So this is one way to visualize that. But that shouldn't stop us from solving this problem. We can solve this problem using our equilibrium equation. So first thing we do is summation of horizontal forces 0. So what are the horizontal forces? Again, there are four generalized force. So when I say generalized force, that includes force as well as moment. And moment could be moment like this, or a torque, or anything else. So generalized force means that includes force as well as moment as a load. So here these are the type of a load as the moment. So it's not moment in, we'll learn about another type of moment called bending moment towards the week 7 onwards, but so far it's a generalized force. Summation of horizontal force 0 means only one horizontal force, which is R1, and that would be equal to 0. What about summation of vertical forces 0? So R1 is not vertical, R2 is vertical. What about 10 kilonewton meter moment? Is that vertical force should come into this equation? Yes or no? No. Whereas R3 should come, so R2 plus R3 is equal to 0. 10 kilonewton meter does not come into picture at all. So R2 plus R3 equal to 0. That means either both of them are 0 or one of them has to be equal and opposite to the other. So it could be 5 and minus 5, or minus 10 plus 10, or they are both 0. These are the only possibility. So R2 is equal to minus R3. The third equation, moment about a point 0, we could again take moment about point A equal to 0. So this will give me moment due to R1 is 0, moment due to R2 0. Now, what about 10 kilonewton meter moment itself? It is acting as a load, so it is acting in a clockwise direction. So that would be needing to consider in the moment direction. So that is plus 10. What about R3? R3 would try to rotate the beam in the opposite direction, to the anti-clockwise direction. So minus R3 times the distance 7 is equal to 0. Now this is the crucial bit, that in the moment equations you need to add any concentrated moment. And concentrated moment doesn't come with the distance. So if this 10 kilonewton meter moment was not at 2 meter but in the midpoint, still this would be 10, because that's the moment itself. You don't need to multiply moment with a distance to get the moment, because that value moment is already there. So that moment is acting at that point. So load you need to convert to moment in the moment equation by multiplying the lever arm. But whereas if something is already a moment, it doesn't matter the distances from the where you are considering moment. So what I'm saying is, if this 10 kilonewton moment was there, this would be still the equilibrium equation. So 10 minus R3 minus 7. So this part, many students in the year 1, first few weeks, find it difficult to conceptualize. How come this doesn't changes with the where it is applied? Now of course it will affect the result in a way how the beam deflects. So on the deflections it will be making a difference, but not in the terms of the reaction forces. So R3 would be then equal to 10 over 7, and going back to the previous equation, R2 is minus R3, so that would be R2 would be minus 10 over 7 kilonewton. So they are equal and opposite, and you could see that's how they will work. Now this moment was any other point onto this structure, still R1 and R2 and R3 would be the same. So the values of R1, R2 and R3 will not change if the location of the 10 kilonewton moment so it will not depend on the moment. Those of you found it difficult, is it clear? Yeah, go on. is anti-clockwise. Moment is clockwise, isn't it? 10 kilonewton meter. Where it is anti-clockwise? It's 10. Oh, if the concentrated moment was anti-clockwise, then I'll put that as minus 10. And then R3 would be positive. So you could see that. You could see that the effect of this moment is to rotate the beam in this way. So that means it will push in this side. So that means reaction from the ground would be upward direction. So that's why it is positive 10/7. Whereas this reaction would be, it is going into that direction. So you need to hold it back to the ground. So the direction of R2 would be negative. Then whatever. So if you are saying that if the moment was in the opposite direction, then it is going up, so the R3 then it would come down.
Instead of concentrating moment, can we give a 5 kilonewton force at the end? Because the distance is 2 and finally the moment at C will be equal to 10.
So what you are saying is, instead of 10 kilonewton meter moment here, if you have a 5 kilonewton load here, then?
Can we divide the 10 kilonewton moment into a force of 5 kilonewton at point A in the upward direction?
Force at this point?
Yeah.
How come that?
Finally, the final moment at C will be 10 kilonewton.
So final moment at this point is C as 10 kilonewton, but is that the same? If you apply a load onto the support, the load would be directly going to that point. So it's not the same. So there will be no share of the. So what you are trying to say is, okay, I like that concept. So you have got these reaction forces, and what you are saying is, I will put a load here of 5 kilonewton. That is giving me a moment about this point as 10 kilonewton. But this load is, it will be going directly through to the ground. So it is not going to affect to the beam at all. So you cannot take the effect of it directly. That's a good question. I'm saying it's a good question because something similar, that the moment is acting at a distance, or when you transfer the effect of the load, there are two things that you have to consider. So if, for example, there was a load like this, and you want to transfer the load to another point, then you have to consider both things. You have to transfer the load as well as the moment. Because this thing, you can consider, the problem is like this way. So I'm just doing the load, okay? I'm just doing the load. So this 5 kilonewton load you have, and I will at this point add 2 more loads, because, and exactly 5 kilonewton. They are equal and opposite, so it doesn't change with this part, okay? So this is exactly the same, because it doesn't change this 5 kilonewton load, so that 5 kilonewton load is there, and this point I have added 2 loads, okay? Now I'll do something interesting. I will consider this into 2 parts. So one part is this load, and one part is the other 2 load. Okay? Now these 2 load is nothing but what you are saying, creating a 10 kilonewton meter moment. But there is this force left. So whenever you want to transfer a force or a moment, you have to see the overall effect. You cannot do just one. Okay, is that okay? But if you could convert 10 kilonewton from there as well, that will not change the reaction forces, but it will change how the beam deflects. This could be point C.
Then the 10 kilonewton moment will not
this is anywhere on this beam. Middle or distant, the moment due to this one could be effect is the same for the reaction force purposes anyway. Okay, thanks. That's a good question. Any other question? Any other point? Okay, if not, I'm going to show you quickly another one. If you have got a triangular load, how do you take into account triangular load? So, which is problem 1F. So, 1F has got towards the end a triangular load. So, triangular load of so this particular one is 5 kilonewton per meter. What do you think? And the total distance is here is 4 meter. What do you think? The question is, what is the total load? Question is, what is the total load? What is the total load if the load is triangular? Yes.
Sir, there is a total load of 20 kilonewtons, which acts 4/3 of a meter from the right-hand end.
Okay, so are you sure it is 20 kilonewton? Because what's the difference if I have, it's at 10 or 20, sorry. 20 kilonewton, okay. So what happens if the loads are like this? All 5 kilonewton. So this side is also 5 kilonewton per meter. This side is also 5 kilonewton per meter. And it acts over 4 meter. So what is the total load here? We have just done that. 5 kilonewton per meter over 4 meters. So this total load in this case is 5 times 4, which is 20 kilonewton. So this cannot be then 20 kilonewton because its one side is 0. So this would be half of that, because imagine this is sort of a full load in that way, 5 kilonewton per meter. Here it is only 5 kilonewton per meter here. So this would be half of 5 times 4, or in other words, the area of the triangle. So that is 10 kilonewton. And this load will act in its center. Similarly, this load will also act in the center of the triangle. So this distance is 4 over 3 meter, whereas this is 4 over 2 meter, or 2 meter in this case. So the triangular load, if you have, or any other load, any load if it is triangular in nature, so find the total area under the triangle, and then it will act at a 1/3 distance from the big side through the centroid. Okay, I think this is it. There is nothing else new concept-wise. And tomorrow tutorial, please look at those problems, 6 problems, 3 for your own disciplines. So there would be for aerospace students, you look at the aerospace plus civil, and then the civil student first look at the civil problem and then the aerospace problem. Thank you. Where you can get up?
Extra question.
Have you finished all of those? And in the statics part, everything you have finished?
I looked at the question before. I did the one that is on.
Okay, but solve the tutorial questions for tomorrow as well. You have done that? Yeah, do those. And then in the textbook. There will be other questions I'll also upload later on, but textbook in the reading list.
Textbook is fine.
Textbook have got lots of questions.
Can I ask a quick? I think you wrote, what was the last sheet of this that you put on the triangle? Yeah, why is it called that?
Because what is the centroid of a triangle? So if this distance is 4, what is the CG, your center of gravity of a triangle? So center of gravity of a triangle.
Is that just a fact?
Yeah, that's a fact.
Okay.
That's a fact. So center of gravity of a triangle. So if this is a triangle, the center of gravity will be somewhere here.
Okay.
And which is, if this length is say 8, then it's not quite there. That centroid CG would be 8 over 3. And if this distance is D, then that distance would be D over 3. That's the centroid of a triangle.
So we're all here for the same thing.
Go on.
Thank you.
What's your question?
I was struggling with question I.
Question I. What was that on?
Trusses.
Or trusses. So just use the same principle in terms of the equilibrium equation. Summation of vertical force is 0, horizontal force is 0, moment downward force.
You don't need to account for like the shape of the truss.
That's the whole point of it is.
Okay.
We will go into that because that will change what are the forces inside each of the member. But when you're calculating reaction forces, it doesn't matter.
Okay. Thank you.
For the recent example, you just give a triangle, right? What if it becomes like a hemisphere, a trapezoid?
Just the centroid. Find the centroid of the same.
Oh, it's like just use.
So we are considering all the loads are centered in its centroid.
Oh, okay. Okay.
Okay? Yeah.
I need some help with some things.
Yeah.
So for this, I can assume it's a flat beam.
Yeah. It doesn't matter. Flat beam, truss, arch. It doesn't matter to calculate the reaction forces.
So I can easily just convert this into a beam and all the forces wouldn't matter.
Absolutely. If you keep the distances right, that's fine. You can think of it as a very thick beam. That's okay.
Okay, so and about this flat beam.
Yeah.
So-
That's called truss, by the way.
Yeah, this truss brace thing. I can assume that the bridge is a flat beam too.
Yeah, absolutely.
Wait, so for assuming that the bridge is a flat beam, I take the 5 kilonewton force and bring it down to the base.
No. You cannot change any dimension. That one is at top of the beam. If you